Let's talk about a time-of-flight data access layer, TDA. And from the end user's point of view, the upshot here is, well, speed. So first, we have large data sizes. And even with centroided data, the data needs to be read from the disk when it's needed. And the next is, if you look at how the data is originally organized in spectral scan order, that makes chromatographic extraction by masses very expensive. And both quant and deconvolution rely heavily on chromatographic extraction. So the upshot here is, in quantitation, we've got our peak extraction, which is a chromatographic extraction, as well as, if you're doing confirmation, we have spectral extraction. The upshot is we have a quant analysis performance that's 5 times faster compared to previous revision with accurate mass data. And with the unknowns, since it relies so heavily on chromatographic extraction, you'll see a speed that's 50 times faster. And you will notice that there's multi-core processing here with the deconvolution approach. So, a couple of caveats. Nothing's for free. I mentioned centroided data. Also the fact that the file size does increase because this is a classic data size performance speed trade-off. So if you look at your data directory carefully, you'll notice that there are new files created, a chromatographic representation and a spectral representation, to speed those up respectively. And the last point is, there's no absolute guarantee that we're going to see the same exact mass if you use different access layers. Let's take a quick look at the time-of-flight data access from a technical point of view. So, the TDA design concept, given to me in these slides from Vadim, stores the abundance data as time-ordered arrays that are indexed by scan number. This is the same idea that was used to speed up unit mass in the indexed data access layer. Now the TOF and QTOF have specific issues that I'll mention here. One is there's lots of mass values, and those are mapped into thin slices that match up with the resolution of the instrument, and that time domain has been changed to, the flight times have been changed to masses. So I can sit here with a particular mass and extract across a retention time, and you can see how with memory mapping I could accomplish a very fast extraction of the masses that I desire in, for example, deconvolution with chromatographic extraction. Let's take a look at this experiment that shows you some of the effects of TDA. So this experiment varies the extraction window. We start with a wide extraction window of 1 AMU down to 100 ppm, 20, and then 5 ppm. So a couple of points to be made here. First, if you look at the time increases when you pick a very thin mass extraction window. You also get a lot more components. And if I look at the match factor, I can see I get a very good match factor here at 100 ppm, tiny bit better at 20, but it looks like a very good compromise here is 100 ppm to get the answers that I'm looking for in a reasonable amount of time. Let's take a look at the question of searching a library with accurate mass data. There's many, many years of experience with unit mass spectra searching against unit mass libraries, and there's a ton of unit mass libraries out there. But what about the question of searching an accurate mass spectra against an accurate mass library with, let's say, precision of 0.01 AMU. Well, the first topic that comes up is I need an accurate mass library. And those are possible. You could end up with exact mass calculations, potentially for fragmentation spectra, and that's a topic for another time. But moving ahead with the assumption that you have an accurate mass library and you run it, well, that will work well. And you can get scores that aren't dissimilar at all from the scores that you would see unit mass versus unit mass. The question is, how many cases does that accurate mass really give you a better score? And you can start to think, well, maybe in the case of an interference, which would not be seen because I've got that resolution. Thanks for your attention.